Alright, welcome to, this is actually chapter 12. The review for chapter 12, alcohols, phenols, ethers, and thiols. I'm going to talk about thiols as well. I noticed some people were not attending lecture. I don't know if they plan to come next week for the test, but just a reminder, this review is not intended to be a replacement for the regular lecture. If there's something on the test that I don't cover on this review, it's likely that it was covered, not only likely, it's definitely covered in the lecture, and if you miss that instruction, it's not my fault. Alright, alcohols contain the hydroxy group. It's called the hydroxy group, or the OH group. Phenols contain likewise well, it's not really a hydroxy group. It's a benzene ring with an OH, a hydroxy group attached to it. Ethers contain the well, it's actually formally is called an alkoxy group, but I'm just going to write it as COC, right? So carbon, oxygen, carbon. And thiols contain what we call a sulfhydryl. I don't believe sulfhydryl, is that how you spell sulfhydryl? I'm not sure about the spelling, but anyway, it's the SH group. Alright, classify alcohols as primary, secondary, or tertiary. Now this is important for reactivity. Why, you may ask? This informs us about their reactivity, specifically in regards to their oxidation products. Put over here products. We'll see more about that in a little bit. So primary alcohol has only one carbon-carbon bond. Has only one carbon-carbon bond, and it will have two hydrogens. Good example, let's put the example up here. Good example here would be ethanol. Okay, so here's ethanol. This is the alcoholic carbon, the carbon with the hydroxyl group, the carbon with the OH, the alcohol group. It has only one carbon-carbon bond. Now you notice it has two bonds here, so it needs two more. Those are going to be two hydrogens. Right? So it's going to be CH2, so it has two hydrogens, only one carbon-carbon bond. Secondary has two carbon-carbon bonds and has only one hydrogen. Good example here would be isopropanol. Okay, so again, this is the alcoholic carbon, the carbon with the bonded to the oxygen, the OH group, the hydroxy group. Notice it has three bonds, so it has room for one more. That's one hydrogen, right? And it has two, we highlight these, it's going to have two carbon-carbon bonds. Tertiary is going to have three carbon-carbon bonds, and the fourth bond then will be to the hydroxy group, so 0 hydrogens. And a good example of this is a molecule called T-butyl alcohol. It's not one that we really talked about in class. We would call this, in IUPAC nomenclature, this would be 2-methyl-2-propanol. Okay, but that's alright. If you notice, this is the alcoholic carbon, and again, it's going to have 1, 2, 3 carbon-carbon bonds and no hydrogens. That's tertiary. Alright, understand how hydrogen bonding influences the physical properties of alcohols. Hydrogen bonding, increasing hydrogen bonds increases boiling points. and solubility. We'll also increase their melting points. Put here N melting points, MP for melting points. Okay. So the thing to remember about hydrogen bonds, in order to have a hydrogen bond, we must have a polar covalent bond, and it's only going to exist in two types, really. We have an oxygen-hydrogen bond, right? So the oxygen is going to be partially negative, the hydrogen is partially positive. And this is, of course, the bond that we see in alcohols, also in water. The other one is a nitrogen-hydrogen bond. And again, the hydrogen is always going to be positive, and these heteroatoms are partially negative. All right. So let me put in the partial negative, partial positive, partial negative, partial positive. The attraction between these two molecules then here in this red dot, this through space interaction, is the hydrogen bond. Here we have two molecules of methanol. In order to boil methanol, we would have to break this attraction. So in the liquid state, we have this hydrogen bond. As we heat this liquid up, this hydrogen bond would be broken. They would go into the gas phase. It would vaporize. It would boil. And this is what needs to be broken. So if we can make this stronger, the boiling points increase. So hydrogen bonds are very strong interparticle force, and that's why alcohols have higher boiling points than, say, alkanes. Solubility over here, we have a water molecule. So just draw a little water surface around the water molecule, around this one as well. When we're talking about solubility, we're talking about, we're talking about water molecules, we're talking about solubility, we're talking about the solubility with regard to water. So what you have to consider here again is the partial negatives and partial positives on these molecules. Oxygen is always going to be partially negative, and hydrogen is always partially positive. And we have this through space, let me use a different color. And this through space interaction, we just line up the partial positives and partial negatives. And then this is the hydrogen bond, the bond between the individual molecules. So if you can form hydrogen bonds with water, it will be soluble. Now, granted, any hydroxy group is going to be soluble, is going to form hydrogen bonds with water, but not all alcohols are soluble. So say, for example, we have this 1, 2, 3, 4, 5. Right? This guy is going to be soluble. We have 1, 2, 3, actually 4 carbons. So I just put C4. But if it's longer, 1, 2, 3, 4, 5, 6, 7, 8, say 8 carbons, C8. This is not soluble. And the reason, of course, for this is you're asking for this little hydroxy group, which is polar, right, to bring this whole, essentially what amounts to an alkyl chain, or the alkane, the hydrophobic part of the molecule, into solution. And this is not polar enough to do that. But if the chain is small enough, it will be. So this way, alcohols less than or equal to 5 carbons are soluble. But once the number of carbons increases, if you only have one hydroxy group, it's not soluble. All right. Dehydration and oxidation. Dehydration of an alcohol is removal of water. This is the reverse of a hydration. In chapter 11, we hydrated an alkene, added water across the double bond, got the alcohol. The reverse of that is removal of water, resulting in either an alkene. And the book also talks about the formation of an ether. Now, I didn't talk about the formation of ether, so you don't need to worry about that. I didn't talk about that in lecture, but maybe I will give you a quick example of this. So let's say we have So in a dehydration reaction, these reactions are also catalyzed by acid. So you might see just a hydrogen ion on the reaction arrow, or they could say H2SO4 is typically what's used, sulfuric acid. So the removal of water, we're going to remove hydrogen and the hydroxide, or the hydroxyl. So of course we're going to remove the alcohol group, but the hydrogen comes off carbon next to it, an adjacent carbon. So here we have the H and OH. That results in the loss of water, and then we form a carbon-carbon double bond between those two carbons. So you notice the carbon that had the OH, right? It has two hydrogens. It still has two hydrogens, but it lost the hydroxy. This carbon, right? It lost a hydrogen, so it has room for just this one down here, right? So we get the alkene. Another example would be the formation of an ether. We'll use ethanol for this, and we'll use a red ethanol and a blue ethanol. Now in the text, they might have a coefficient of 2 in front of these alcohol molecules, but you don't have to worry about that. I just wanted to show you when they're talking about this in the book, you're going to lose a hydrogen and a hydroxy, but not from the same molecule, but from two adjacent molecules. Now remember, this is, say, rolling around in the liquid state, so these two guys bump together and we remove the hydrogen and the hydroxy group from two different molecules. So what's left, these guys condense and we form the ether, and of course plus water is lost. All right. This reaction I did not speak of in lecture, so I won't hold you to it on the test, but certainly the dehydration, right? And also, that was chapter 12. Remember, chapter 11 is the hydration. So this reaction is reversible. We could go back the other way, add water across that double bond, and get the alcohol. All right, the other reactions we talked about for alcohols was oxidations. Oxidation of an alcohol is the addition of oxygen. So you form carbon-oxygen bonds, or the removal of hydrogen. Okay. The products are either an aldehyde. Okay, and then it says here, depending upon whether the alcohol was primary. So if it's a primary, you form the aldehyde. So the products are either an aldehyde if it's primary. But remember, the aldehyde can be further oxidized, put a little O here for oxidation, to a carboxylic acid. That's if it's primary. First to the aldehyde, then to the acid. If it's secondary, it can be oxidized to ketone. And if it's tertiary, no reaction, NR, no reaction. Provide some medical uses for selected alcohols. I did talk about this a little bit. Primarily, the use of alcohols is limited to phenol and isopropanol as disinfectants. So I talked about phenol or carbolic acid or Lister's reagent, right? Those all different names for phenol as antiseptic, disinfectant or antiseptic. And you're probably familiar with alcohol wipes being used before getting an injection or something like that, and that's rubbing alcohol, which is 2-propanol. Ethanol, I did mention this briefly as well. This is the antidote for ethylene glycol poisoning. Ethylene glycol poisoning. Ethylene glycol, if you remember, is antifreeze. Methanol, there is no medical use for methanol. It's toxic and it's not good. We did also talk about the medical use of ethers. Ethers are used as anesthetics. So the general anesthetic, the first general anesthetic was diethyl ether, or simply ethyl ether. Okay. No common and secular names for the alcohols listed in number 5. Right. So phenol is also known as carbolic acid because it is acidic. I'll draw a quick dissociation reaction. Right. We lose this hydrogen here on the end, and we get this conjugate base plus the hydrogen ion. And like I said in the lecture, it's about 1,000,000 times more acidic than most other alcohols. It's also known as Lister's reagent because Dr. Lister was the first one to use it as an antiseptic. Ethanol, actually ethanol can also be used as a disinfectant, but usually 2-propanol is instead. Ethanol is known as, the common name for ethanol is ethyl alcohol. Right, that's a common name. The secular name or the nickname is grain alcohol because it is derived from the fermentation of grains. It's the potable stuff, the stuff that we find in beer, wine, and distilled spirits. 2-propanol has actually a bunch of different names. It's also known as sec-propanol. Sec-propanol because it is a secondary alcohol. It's also known as sec-propyl alcohol or isopropanol or isopropyl alcohol because it has an isopropyl group attached. Let's draw the structure. I know I drew it up there before when I was talking about secondary alcohols. Right. So there's the structure. This is the isopropyl group, right? 3 carbons, but it's the little Velcro tag here that's attached to the alcohol group is on the second carbon, not on the end carbons, but on the middle carbon. Right. So this is isopropyl group, isopropyl alcohol or isopropanol. This is also known as, the secular nickname is rubbing alcohol. So look at all these different names for the same molecule. Crazy. Identify the thiol functional group and a disulfide bond and the results of the reduction of a thiol bond. So that's actually all right. Identify the thiol functional group, a disulfide bond, and the results from the reduction of a thiol bond. Thiol contains, we mentioned this up at the top, the SH group is called the sulfhydryl group. Oxidation of a thiol does not produce like the aldehyde and ketone that we saw with the primary secondary alcohols. Instead, they form a disulfide. Disulfides are 2 sulfurs bonded together like this. And I did mention that these thiols are found in proteins. I mentioned how it's in connective tissue, proteins like collagen are found in hair and skin and whatnot. Thiols are found in proteins where they, I'll just say for right now, we haven't really talked about proteins at all, but I want you to understand that they are found in proteins where they reinforce and make, let's say, protein structures stronger. So when we do get into the chapter on proteins, you'll have some idea of the thiols. You'll see how many, there's different types of proteins. Some are structural and they need to be, obviously strong, so they have disulfides. Other proteins are extracellular, so they're outside the cell and they need to be strong because they're in kind of an unfriendly environment and they need to be pretty sturdy, so they have these disulfides as well. The last thing here is thiols stink. Okay, many of the thiols have a unpleasant odor. on a rotten egg or sulfur odor. Let's look at some of these oxidation reactions. In particular, now we've got some space here. A primary alcohol. All right. First thing to remember here is a primary alcohol is always going to be found at the end of a chain. Right. So we have 1, 2, 3, 4, 5 carbons alcohol. If we oxidize this, 1, 2, 3, 4, 5, this becomes an aldehyde. And if you remember, aldehydes end in hyde. You can think of that hyde as a hydrogen. Now I'm going to put this carbon here. Right? Look at that carbon. It's got 2 bonds to the oxygen, 1 back to the rest of the molecule. So there's a carbon-carbon bond here. That's 3 bonds. It means it needs 1 more, and that's the hydrogen. So aldehydes have that hydrogen. Aldehydes can be further oxidized. You have 1, 2, 3, 4, 5. Remember, oxidation is a gain of oxygen, so we had 1 carbon-oxygen bond here. Now we have 2. We also lost a hydrogen. We lost this hydrogen on the OH. So oxidation is a loss of hydrogen, the gain of an oxygen. So we gained another carbon-oxygen bond. And the second oxidation here, we're going to stick an oxygen in between this carbon and oxygen here. Let me use that. So we get the carboxylic acid. All right, that's primary alcohol. Secondary alcohols. Secondary alcohol is going to be somewhere in the middle of a chain. 1, 2, 3, 4, 5 carbons again. Let's put him here, right smack dab in the middle. If we oxidize this, we get 1, 2, 3, 4. We're going to form the double bond here. This is now a ketone. If you notice, the carbon here, that what we call a carbonyl group, right? This carbonyl carbon. Carbonyl is a carbon double bonded to an oxygen. It already has 4 bonds, no hydrogens. Right? So no hydrogen, so it's not can't be oxidized further. If we try, get no reaction. So secondary alcohols get oxidized to ketone and stop. Tertiary alcohols, if you recall, they don't get oxidized at all. Now for thiols, we talked about the oxidation of thiols. So thiol, it's kind of like an alcohol but has an SH, right, instead of an OH. And what we're going to do is we're going to take, it's kind of like the ether business that I talked about. We're going to take 2 different, or I should say 2 individual molecules. They happen to be the same compound. This would be ethane thiol. Right, 2 carbons is ethane. We have a thiol group, so ethane thiol. We take 2 of these guys, and if we oxidize them, what we really do is we lose a hydrogen. So remember, we're going to lose a hydrogen. So the 2 hydrogens we lose are these guys, right? Those 2 hydrogens. And what we end up getting, right, so we have the CH3, CH2, the sulfur stays. So that was the purple molecule on the left, plus this red molecule on the right. And we form this sulfur-sulfur bond. We form this sulfur-sulfur bond, and we link the 2 thiol molecules together in what we call a disulfide. So here's a oxidation in one direction. We'll put hydrogen here. In the reverse direction, use blue for that. In the reverse direction, this would be a reduction. This is where we're adding hydrogen back and reducing this disulfide back to the thiol, adding hydrogens back onto these. So this is a this is a form that you see in proteins, where one strand of an amino acid chain or a protein chain is linked to another strand by this disulfide, and that's what helps hold these proteins together. Okay, so it's quite a bit different from what you saw in the oxidation of alcohols, where we formed a carbon double bonded oxygen. There is no double bonded sulfur. Instead, we form a sulfur-sulfur bond. So this is the disulfide. Okay. So I hope this helped. You study hard, do well in the test. Good luck.